speaker is Professor Wataru Souma, who is going to talk on the study of early warnings indicator of financial crisis.
Okay, thank you, Mr. Chairman, and thank you, organizers. Title of my presentation is Study of Early Warning Indicators of Financial Crisis. This study is a collaboration with Hiroshi Ietomi at Niigata University and Hiroshi Yoshikawa at Rissho University. This research was supported by MEX Exploratory Challenge on Post-K computers. So, anticipating financial crisis is a very important problem. So, to anticipate financial crisis, early warning indicators of financial crisis very important. So many central bank and national government, national institutions try to find such a kind of indicators. So, for example, BIS and IMF and the Bank of England find and search these indicators based on their experience. For the case of Bank of Japan, there are two types of early warning indicators. One is the Financial Crisis Index. This is proposed by this article. This article is written in Japanese. In this article, they choose the 19 indices, and these 19 indices were separated by two groups, leading and lagging two groups. So these two groups, the author of this paper defined it the two indices. This is the same concept of price indicators. But in the case of price indicators, there are three types of indicators: leading and coincident and lagging. But in the case of financial indicators, there are only a leading and lagging. Okay, so the other is the financial activity indicator. This is proposed by this article. In this article, the authors chooses from the 159 indicators from 152 indicators to 40 indicators they choose. So today's my presentation, I focus on this part, 19 indices and two groups. So explain these are 90 indicators proposed by Bank of Japan. Well, in this table, topics are sector banks and real estate and construction. These are monthly data. So there are 33 type of sector indices, but they only choose three sector indices. Okay. Another is the company's cash flow, bank's leading attitude, and farm profit, housing loan. These are quarterly data. So, and commodity market condition, this is a monthly data. These are leading indicators. So another indicators, household debt, company debt. These are quarterly data, and loan interest rate is a monthly data. Farm borrowing interest rate are quarterly data. And M2 and M3 and deposit balance is a monthly data. Land price are nationwide, and land price big city, these are same year data. Okay. Japanese government bond yields 3 years and 9 years also monthly data. So maybe you have a question. How to divide these 90 indicators to two groups, leading and lagging? So to separate two groups, they apply the Hodrick-Prescott-HP filter method. For example, this is a time series or TSE sector index banks. They use the values at the end of month, like this. This is from 90 1983 to 2016, like this. This is the original data. So by applying HP filters, they obtained these figures. So in this figure, a solid line is important. A dotted line is the only slope of these solid lines. Okay. So for this filtered result, they applied such an analysis. For example, a peak is here and here and here, and 3 peaks have. So in Japanese asset price bubble happened 1990, January 1990. This is called the Heisei bubble here, okay. And this figure is, this axis is correspond to this. Here is 97 to the 93 and so on. This here and here. So this peak, this January 1990 corresponds to here, and another bubble happened. This, the left side is leading, meaning leading, and right side meaning lagging. So, okay. So another type of financial crisis, the chain bankruptcy of Japanese banks. This is happened November 1997 here, and so this is here. So the peak, the position of the peak is here. Here is correspond to here. This is the position of the peak, and another peak is here, or this is here, and so cross section is here. Yeah. So in this case, banking sector index is leading and leading. So this is a leading indicator. So they applied 33 sectors. So they find such figures, leading, and so this dot corresponds to the leading indicators, and this is correspond to the from the viewpoint of the Heisei bubble. These are leading, but from the chain bankruptcy, these are lagging. So this is these sectors are impossible to use predict financial crisis. So they use these the leading indicators. So such a way, based on 2 financial crises, and Kamada et al. Defined the leading lag relationship between 33 TSE sector indices. However, we expect that the lead lag relationship between 33 TSE sector indices will change frequently. So another case is here. This is Japanese government bond, 3 years. In this case, peak is here and peak is here. So the cross section is here. This means lagging and lagging. So this index is lagging. So by using such a method to 19 indices, they make these figures. From this figure, these correspond to the leading indicators, and these correspond to the lagging indicators. But based on 2 financial crises, Kamada et al. Defined its lead lag relationship. But I think the 19 indices, the lead lag relationship, 19 indices change frequently. So return back to this 90 indicators. So in this my presentation, I want to modify first this part, because they use monthly data of stock index data. So, but as you know, such a value of index changes millisecond or tick by tick. So to use monthly data is a mistake, I think so. So, and I explained the previous slide, leading lagging is not so stable. I think leading and lagging relation changes frequently. So this is my motivation. So the first is we would like to get effective monthly stock indices from daily fluctuations and correlations between 33 TSE sector indices. This is the first motivation. The second motivation is to get the answer is for the question. Is the lead-lag relationship between early warning indicators stable? So to overcome these two problems, we apply complex Hilbert principal component analysis. This is short CHPCA. The CHPCA is firstly proposed by Rasmussen in 1981. This is the atmospheric science field. So mainly this CHPCA method developed in atmospheric science field. But recently, maybe Ietomi et al. 2011 is the first paper to apply the CHPCA method to the econophysics. And next, Bodenska and I wrote paper and Aoyama et al. So why we apply CHPCA? This is because the advantage of CHPCA is we can easily analyze the different time correlations. So we can easily analyze the lead-lag relationship between time series. So the first part. So we applied the CHPCA to 33 TSE sector indices and topics. These are shown in this figure. So we assign number from 1 to 33, and we assign number 34 for topics. So we analyze 33 TSE sectors and topics, 34. So the time series is shown in these figures. This is daily data. So from the time period is from January 1983 to December 2015, 16. So the total day is 8,571 days. For these data, we apply CHPCA. So I explained how about the complex correlation matrix. To apply CHPCA, we have to define the complex correlation matrix. So firstly, we define the log return. This is we use daily data. So in this case, log return means the closing to closing log return of sector J at T day is defined by this equation. Here, SJT is the closing value of sector J at T days. So SJT minus 1 is also closing value of sector J at T minus 1 days. So here, J is runs from 1 to 34, and 34 corresponds to the topics. Okay. So in this case, T is runs from 1 to capital T. Capital T equal to 8,570. Okay. So log return is defined by this equation. And this equation is a Fourier transform of the log return. Okay. Here, omega k is defined by like this. This is a Fourier transformation. Next, we define the Hilbert transformation of log returns. Hilbert transformation is shift the phase of the RJT here by only half pi. Okay, so sign of this here is a minus and so on. So by using this log return and this Hilbert transform, we define the complex log return like this. Yes. R tilde JT, here is a JT is defined by this. This is the original log return, and plus I is the imaginary unit, and R hat is a Hilbert transform. So this is also written in like this. So okay, so log return is a real data describes the change in real space, but this complex log return describes the change in the complex place. So, okay, this is the real value, but the real value project to the complex plane. So we regard the change of R as a change of amplitude and phase in complex space. Okay. So here omega k is defined by this, and omega k is positive. So as time goes by, this rotates counterclockwise direction. Okay. This is the definition of the complex log return. By using this complex log return, we define the monthly mean value of complex log return like this. Here, Tm is identified months. As I explained, T runs from 1 to capital T. But this is also divided by the 408 months. And this capital T1 to T100, 408 identifies the months. Okay, for each month, we calculate mean value of complex log return. So same way, we define monthly variance of complex log return like this equation. In this case, we are considering a complex variable, so this is absolute value square. Okay. So by using these two mean value and variance, we normalize the complex log return like this. So by using this matrix, this component, we can define the monthly normalized complex log return. Monthly matrix like this. So by using this WM, we can calculate the monthly complex correlation matrix by this equation like this. So that we have 408 complex correlation matrices. So for each complex correlation matrices, we apply the PCA. Okay. So this is distribution of eigenvalue. This is an example of April 1981. So this red line, this is explained by previous speakers, Marchand-Pasteur distribution, given by this equation. Okay, the Q is defined by like this, and here lambda plus minus is defined by this equation. So in this Marchand-Pasteur distribution, plus means this equation. If x if x is positive, and that case x is selected, but if x is negative, we choose 0. Okay. So characteristics is this lambda 1. This is so-called market mode. Okay. And another characteristics is here is lambda equals 0. This is a peak. Why such a peak appear? This is because we are now considering n equals to 34, and Tm length of monthly data is 18 to 26. So in this case, Qm defined by this is larger than 1. So in this case, this is a positive value. So this data function is survived, and so here a peak appears. So this means the rank of CM tilde is smaller than 34. So such a reason zero eigenvalue exists. So this is the animation of the change of the eigenvalue distribution. So this is the largest eigenvalue, and this is the Marching pass-through distribution, and always lambda 1 is greater than upper bound of Marching pass-through distribution. So market mode is meaningful. So from this animation, we can say that the largest eigenvalue is always meaningful. So it is reasonable to consider the eigenvector of the largest eigenvalues. This is the example of April 1991. In this figure, blue dot is the topics. So to calculate the eigenvalue, we set the constraint that the topics is takes real values, not the imaginary value. Okay, so topics exist on this real axis, and these red lines correspond to 33 sectors. So as explained previously, as time goes on, complex log returns rotated counterclockwise direction. So in this case, this direction means leading. And other direction, this direction is lagging. Okay. So in this case, topics is a benchmark. And compared to topics, these sectors are leading sector. And these sectors are lagging sector. So this is also show animation from 1983 to the 2015. So as I explained, topics always exist on real axis, and blue dot and red dot correspond to 33 sector indices. 36 sector indices moves rapidly, and sometimes suddenly broadly distributed and converge to and so on. So this animation shows the lead and lag relation change frequently. Okay. Okay, stop animation. So to quantify the lead and lag relation, we set the total phase difference by this equation. So this is, as I explained, the topics, the phase of topics equals 0 because the topics is always real value. And then topics is a benchmark. And from benchmark, we measure the phase, theta. So total phase difference is defined by absolute value of the this part. So, but in this case, topics theta 34 equal to 0. So we only add the absolute value of 33 to phase difference. So okay. So now we explain for the case of 1 month. In this case, QM is greater than larger than 1. In this case, rank is smaller than 34. If matrix is full rank, if a matrix is full rank, rank is 34. But in this case, QM is larger than 1. So rank is almost 10. And this figure shows the change of lambda 1. And this figure shows the change of total phase difference. Right-hand side, right panel shows if we calculate the 4 months interval. So in this case, if we define the complex correlation matrix 4 months, and in this case, rank is 34. Okay, so this figure, even if we take months equal to 4 months, lambda 1 change like this, and theta change like this. Behavior is not so different. Okay, so comparing these two these figures, we can observe that when lambda 1 is large, total phase difference theta is small. Okay, but lambda 1 is small, theta is large. So we can take a scatter plot of lambda 1 and theta. As you can see, this figure shows lambda 1 and theta are negatively correlated. So this is Kendall tau. Kendall tau is, in this case, minus 0.7, and in this case is minus 0.64. From these figures, we can say that the maximum eigenvalue and the phase difference means the lead-lag relationship are inversely correlated. So I think this is one type of hard behavior. This is very simple result. And okay, when a market is explained by the largest eigenvalues, in that case, 33 sector move same way. But if we cannot market as the largest eigenvalue, in that case, 33 sector move differently. Okay, to summarize my presentation first part, we started these 33 TSC sector index. This data is daily data. But by applying CSPCA, we get monthly data. But only lambda 1 and theta is meaningful. So this is a kind of, I think, a renormalization. Okay, there are 33 and daily, but in this 33, but by applying CSPCA, this means renormalization. We get two index, and two index. These are monthly data. Okay, so the second part of my presentation is to apply our result to the a prediction of the financial crisis. So this is previously shown Bank of Japan's 90 early warning indicators. So we modify this part to the lambda 1 and theta. We obtained we newly obtained values, indicators. Okay, so bank's lending attitude is quarterly data, but I think this data is corresponding to the Citibank's data, loan and bills discounted. This is the monthly data, and Citibank's total asset. This is monthly data. So we use instead of this data, these monthly data as early warning indicators. And so company debt is also quarterly data, but we use the number of bankrupt companies and liability amount. These are also monthly data. So M2 is monthly data, so we use M2 money stock, and this land price nationwide and land price big city semi-year data, but we use real estate price index. We can get monthly data for the residential areas and detached house. So we use these two data also. So JGB is 3 years and 9 years monthly data. So we use these data. So in addition, we use national government debt. This is also monthly data, and effective exchange rate. This is also monthly data. So we use total 30 indices. So case one, we firstly consider the Japanese asset price bubble. This happened January 1990. So by using 2 years before data, we calculate the complex correlation matrix and apply CHPCA. So we investigate the distribution of eigenvalue and the eigenvectors. So this is the distribution of eigenvalues, and this red line is Marchenko-Pastur distribution functions. In this case, largest eigenvalue, this is meaningful. So it is meaningful to consider the eigenvalue corresponding to largest eigenvectors corresponding to largest eigenvalue. So in this case, the distribution of the component of largest eigenvector is shown in these figures. So to calculate these eigenvectors, we set constraint lambda 1 is always located on the real axis, okay, lambda 1. So in this case, lambda 1 is the benchmark. So compared to lambda 1, these indices are leading indices, okay, and these indices are lagging indices. So as explained some slides ago, lambda 1 and theta are negatively correlated. Reflected to the such a difference of the position. Okay. So, but maybe this is the weak point of the CHPCA. It is very difficult. For example, if some indices located here and located here, and this, for example, this index is a lagging value, and but this is a leading value, but the phase difference is very small. So in this case, lambda 1 is a benchmark. So we restrict to the phase to this range. Okay, from plus half of pi to from minus half of pi. So we discuss only this range. So next, we calculate after 2 years of Heisei bubble and obtained such a distribution of eigenvalue. So in this case, it's also a red line is correspond to the Marchenko-Pastur distribution. So from the application of random matrix theory, this largest eigenvalue is regarded as a noise. But from the viewpoint of PCA, this largest eigenvalue is also meaningful. So it is meaningful to consider the largest eigenvector of the largest eigenvalue. So the distribution of component of largest eigenvector is shown in this figure. So in this case also, we ignore this range. Okay. So these leading indices indicators, and these are the lagging indicators. So comparing before and after, we get this table. Okay. So this is a before, this is a after. So before the Heisei bubble crash, Citibank and loan and bills and total asset and JGB is a leading parameter indicators. And also real estate, residential and real estate house is also a leading parameter before the bubble. So before the bubble, money stock and government debt and number of bankruptcy are lagging, and this liability amount is also lagging. But after the crash, these are also leading. But this real estate, residential and real estate house changes from leading to the lagging. So this means that in the case of Heisei bubble, real estate, residential, and real estate house is maybe the early warning indicators. So maybe you have a question. If we use topics instead of the lambda 1 and theta, so what happens? So if we use topics, and for the case of the Heisei bubble, distribution eigenvalue is like this, and distribution of eigenvectors is like this. So we ignore this range, and in this case, topics is a benchmark. If we use topics as a benchmark, we only 4 indices are reading, and there is no lagging indices. Okay, so after 2 years of the Heisei bubble, only 1 indicator is a reading. So if we use topics as a benchmark, we only expect we only only can find this value, this index. So from the point of view economics, this is meaningless. So I think to use the topics as a benchmark of financial crisis is meaningless. So this is a case of the chain bankruptcy of Japanese banks. This is happened December 1997. So we repeat the same calculation before 2 years. In this case, eigenvalue distribution is like this, and eigenvector distribution is like this. So we ignore this range, and liability amount, government debt, number of bankruptcy is the leading indicator, and another money stock and Citibank the real estate. These are lagging indices. So after 2 years, we ignore this range. In this case, leading is the liability amount, lagging is government debt and real estate and number of bankruptcies. In this financial crisis, liability amount is leading, but the number of bankruptcy of government debt is changes from leading indicator to lagging indicator. This means that in this bubble and in this financial crisis, a number of bankruptcy and government debt is early warning indicators. So case 3 is this is Lehman shock. Same calculation repeats. In this case, is also these are leading, these are lagging. So after the crash, these are leading and these are lagging. So in this case, maybe a number of bankruptcy is a candidate of the early warning indicators. So summarize my discussion. We started the 33 TSE sector indices. These are daily data. So we apply the CSPCA, we get the lambda 1 and theta. These are monthly data. This is a kind of the normalization. So in this case, lambda 1 is a market mode and theta is a total phase difference. So we find that the maximum eigenvalue and the phase difference real relationship are inversely correlated. This is one type of hard behavior. This is new finding. And financial index monthly and lambda 1 is monthly. The real relationship between early warning indicators is not stable. We studied the 3 types of financial crisis. For these 3 types of financial crisis, candidate of early warning indicator changes. So this is a near future work. There are many economic indices. We consider only the early warning indicators. So financial sectors monitor early warning indicators. So for example, BIS and FRB, BOE, Bank of Japan execute a macro stress test. But I think news is also very important. News is also become early warning indicators. So we apply natural language processing, and this means apply naive-based classification and RN, recurrent neural network, and convolutional neural network. These are deep learning method. So by applying news, we will make macro sentiment index. Macro sentiment index means the mood of the society. So this macro sentiment will become one type of the early warning indicators. So including these one early warning indicators, we extend such a kind of macro stress test. So happily, in Japanese case, we have trade data of farm networks, and also we can get the lending relationship between financial sector and non-financial sector. So we can extend the Bank of Japan's macro stress test on post-K extend macro stress test and simulate on post-K computer. Okay, thank you very much for your attention.
Thank you, sir, for such an interesting talk. Any question from audience?